Good morning, everyone. My name is Sharantaya from first semester CSC AML. Today, I'm going to tell about photonic crystals of lighting applications. The core theme, as you see on the slide, is the photonic crystal represents nothing less than the future of lighting. For decades, lighting has been dominated by traditional bulbs, then fluorescent tubes, and now LEDs. But a new material is operating at the nanoscale, is poised to offer unprecedented informative control over light. Over the next 15 minutes, I will introduce you to the revolutionary metal, explain its core physics, and detail its advantage of traditional system, and look at the challenges road to commercialization. What are photonic crystals? So let's start with the fundamental questions. What exactly photonic crystals are? Photonic crystals are essentially periodic nanostructures. Think of them as material structure to control the manipulate light flow. The analogy often used in physics is that they affect the motion of protons or light in the same way a semiconductor crystals affect the motion of electrons. The mechanism for this control is a property called photonic band gap. Just as a semiconductor has an electronic band gap, the photonic band gap is a physical range of frequencies of colors of light, where light is forbidden and simply cannot propagate through the material. By precising engineering this gap, we can dictate exactly how light behaves, where it goes, what color it is, and what direction it takes. This leads to high efficient and customization lighting solution. The core principles photonic band gap. To understand we achieve this precise control, we must look at the three pillars of the photonic band gap. Periodic structure are composed of materials with alternate layers of high and low refractive indices. Critically, these layers arranged in repeating pattern at the scale of lighting's wavelength. This nanoscape arranged in crucial light manipulation. This precise periodic structure is what creates the photonic band gap, preventing light within the specific frequency range from the passing through the crystal. It is a complete internal material based on control mechanism. And third one is customized control. The beauty of this material is it's tunable by adjusting the crystal lattice constant, the spacing between the layers and its material composition design can be precisely tuned the band gap to control light color, direction and intensity. This ability to control the light at the nanoscale is what it makes the technology revolutionary, fundamentally moving us beyond the traditional external components like filters and reflectors. Traditional lighting versus photonic crystals. The advantages of photonic crystals are best highlighted by a direct comparison with conventional lighting, whether that is old fluorescent technology or modern LEDs. PCs address the key issues like energy waste and poor lighting quality. Energy efficiency. It is good but limited by external losses and heat generation. Exception. Near perfect light extraction and minimal waste energy. Color control, achieved via phosphorus or filter leading to energy loss and color shift, and directly controlled by nanostructure, resulting in pure, stable, and tunable colors. Directionality, it requires bulky external optics like lenses and reflectors. Intrinsic directionality, light emission, can be precisely steered without external components. This intrinsic nanoscale control is primary driver of efficiency and quality. Key applications in luminance. Beyond simply boosting existence of LED PC enable entire new classes of illumination. High efficiency LEDs. As we noticed, PCs dramatically improve light extraction efficiency, reducing internal reflection and boosting overall brightness and lifespan. Tunable white light. This enables the creation of smart white light source. The source temperature and spectrum can be dynamically adjusted to mimic the natural daylight. This is critically for the next topic, CDN lighting. And third one is vibrant displays. PCs are used in advanced display technologies like micro LEDs to create purer, more saturated colors with significantly higher energy efficiency compared to current OLEDs and LCD screens, enhancing LED performance. The most intermediate and commercial relevant impact of photonic crystals is overcoming the fundamental efficiency limit of current light emitting diodes. The problem is external reflection. In standard, LEDs a significant portion of generated light is actually trapped inside the high refractive index semiconductor material. This wasted light turns into heat, reducing efficiency. The elegant solution in PC integration, a photonic crystal structure, is a precise pattern onto the LED surface. This structure acts as a diffraction grating, achieving enhanced extraction. It scatters the trapping light, redirecting it out of the chip and successfully increasing overall light output by an impressive to 50%. The promise of circadian lighting. This is actually arguable the most exciting application from a human-centric perspective. Photonic crystals are crucial for next generation human-centric lighting systems are directly support the health and productivity, mimicking natural spectrum. PCs allow light sources to shift their spectral output throughout the day from cool, blue-rich light in the morning to warm, amber light in the evenings. Crucially, they do this without relying on insufficient color mixing. Optimization, well-being. By proving this exact light spectrum needed to be at different times, these systems can regulate the production of the sleep hormone melatonin. This in turn can significantly improve their sleep quality, alertness, and mood in environments like office and hospitals and homes. This is truly light tailored to human biology. You can look up and emphasize the importance of human being. Manufacturing and commercial challenges. Despite the vast potential, scaling up photonic crystals technology faces significant hurdles in fabrication and cost. The nanoprecision. Creating the necessary periodicity structures requires extremely high precision lithography and etching techniques. These methods are inherently expensive and difficult to execute uniform over the large. The material integration. It is complex engineering challenge to seamlessly integrate the PC structures with existing semiconductor material like gallium nitride for LEDs without introducing defects can reduce performance. Cost of production. Currently, the high manufacturing cost limits PCs primarily to high-end applications. To make the technology commercially visible to generally lighting, the new cost-effective mass production methods must develop. The row ahead research and development. Currently, research is intensively focused on overcoming these manufacturing barriers and exploring new excitement applications for lighting controls. The first one is self-assembly techniques. Researchers are developing colloidal self-assembly methods to create large area PCs cheaply and efficiently, moving away from the expensive top-down lithography methods. The second one is photonic crystal fibers. This involves creating fibers with PC structures in the cladding to guide light with unpredictable laws, which is evolution, telecommunication, and sensing. And third one is solar energy enhancement. PCs are most being used to trap light with solar cells, increasing the light absorption path length and significantly boosting the overall efficiency of photovoltaic devices. And conclusion, a brighter, smarter future. To conclude, the evidence is clear. Photonic crystals are the foundation for the next generation of lighting. By offering precise nanoscale over the light pieces promise lighting solutions that are not vastly more energy efficient but can fundamentally smarter and more tailored to human needs. We project this technology can deliver a 50% potential increase in LED light extraction efficiency, an expected 10x lifespan increase for PC enhanced light systems, 100% level of control over light color and directionality. Photonic crystals represent a pivotal step in engineering the light we live under. Thank you for your time.